the last talk of the day, visiting Leonardo Cavenaghi, interesting recording. The second talk will be about the Hodge projects.
Okay, so thank you very much for attending for one talk. And it's last talk in the morning, so it's very nice. And I'll continue to talk about this Apollo's story. And today we really want to try to make it clear what is the variational geometry aspect of the theory, and we maybe see some examples. I mean, I prepared more views, but I really don't want to go there, but in case there's questions, I think should be all right. So yesterday, we discussed the concept of and bundles, but for the sake of computations and many other stuff, what shall we really need is this residual structure. So in the setup, throughout the lecture, we shall consider X over C smooth projective. Okay. Then we pick this non-Archimedean field here, these visual series. We set H to be the best homology of X, Q, and then simplify. That's right over Q. Okay, this data. Then there was this A model at bundle. This comes from Gromov-Witten theory. And in essential, what we have in this context is you have some vector bundle. Oh, by the way, you're gonna always see this with its natural Z2 grading. That is why we are always referring to super stuff everywhere. So this is a analytic super vector bundle over B X cross E, where I just recall that EX you can see as some parameter space for quantum multiplication. And then B was a germ of a K analytic disk with formal coordinate. And of course, all this data had a flash. It was flat, possible some fold when you equal to 0. So the residual quantity that you have out of this was the super manifold. That is safe if you think that this is the parameter space to your quantum multiplication. So which choice of point here? You have, I mean, all this data implied that the tangent space would actually be identified with H, K, and with your multiplication on this one. And there was some vector field. Let's call this Euler vector field on spot B. That plays some kind of I mean, it's okay if you really want to see this as Frobenius in some Macmillan setting. So this should be the same on the vector field. But mostly we're interested on this kind of operator that assigns to its B. Precisely, this is a vector. So we have a multiplication. So it makes sense to consider this guy here. That you can see an endomorphism of this residual guy. Now, here comes where the atoms shall play some role. I mean, it's completely alright to think about this kind of geometric picture. You have some moduli space, and then you have your quantum multiplication. So the tangent space of this moduli space, this parameter space, is a copy of your homology, but with coefficients on this non-Archimedean field. And the structure product there, to each point, is that given by the deformation of the quantum multiplication. Now, what happens is, if you remember that you have this category of a Q polarizable pure Hodge structures, please accept this as a fact if you know this, but this category here, where you collect like a union of pure polarizable pure Hodge structures, it's a representation. It's a category of representations of a certain group. So this guy here is actually the category of representations of a group that will denote by MT-com. This is what appears in the literature by the name of Monfortet. Now, if you consider now not only polarizable, when we consider still this, but Z2 graded, the same happens, and we convention that we take this common. So my point is, whenever you collect Q polarizable pure Hodge structures that are Z2 graded, this is a category of representations of a certain group. This group here is what we'll call Monfortet group. Okay. So one important aspect of this is the following. This group is raw reductive, which I like to understand that it's good to split the representations. So what happens is Monfortet group, it acts on your homology. For instance, the fixed locus is the subspace of Hodge classes. Now, if we extend the scalars of this Monfortet to this non-Archimedean set, it will also act on our GX, because this is the parameter space that's built out of the data from homology. This is pretty standard in Gromov-Agent theory. So inside of this VX, we can look to the fixed point set. Let's call this VX empty.
What is that? VX?
Sorry, this is MP, but then you extend scalars to the non-Archimedean field. MPK. We have that. So we can look to the fixed point. Now, what's going on is the following. These are fixed points, right? So we have the action is still on this guy, but if you take then the derivatives of this action, you get this isotropy representation. Okay. So one important aspect is then these representations. So what I mean is the following. Let's write this in blue to refer that we are there. So for all B that you pick on BX and T, differentiating the empty action yields to some endomorphism. DB. Now we have two different endomorphisms. We have this one, and this one. One that comes from the action of the Monfortet group, and another that comes from the quantum multiplication. The point about atom theory that you're going to get there is that these two are compatible. So precisely what atoms shall be are representations of the non-particular group that comes from a splitting given by the Riemann-Witten theory. Let's make this precise. And I mean, that's why it works in terms of to try to produce stuff in variational geometry. This is one of the aspects why this works. Yeah. These two, so we have these two endomorphisms. Now we are going to look to possible splitting stems. First, this is a pro-reductive group. So it decomposes representations of the non-particular. These guys, these endomorphisms, are just representations of the non-particular group, right? Because it's the action, the differential of the action. Now this guy can be split and produce a split in terms of eigenvalues for like generalized eigenspaces for his operator. The point is that they commute. So this piece of Gromov-Witten, they can be written in terms of the sums of the representation of them. Let's make this precise, or more precise now. So now there is a claim. Let's go more to your question. That is the core of this story. So there exists some admissible open right here inside of this BXMT where the number of eigenvalues of kappa B is maximum. Such that the number of eigenvalues is maximum. Okay. Then we come with a lemma. This is do Katzerkov concept until in U. That's the following. So pick B here on this U. Then look to this decomposition of H0 B, right? BB BX into the generalized eigenspaces. Let's call it CB. Yes. Maybe it's not good to see. I'm right again. So you pick some B inside of this BX G. Then you look to the eigenvalues of this operator. Then you have a decomposition like this. So B is H0. This is Dx. This is what we had before, but then we look to the decomposition in terms of the guy in the spectrum. So the collections of lambda are eigenvalues. Eigenvalues of kappa B. Okay.
Is B in U or in general? Because it seems that you restricted to this U. Here it's in U and there it's in BX.
Is only U.
So what is this U? Can you tell us more? Is it?
Yes, I can.
Is it a dimension or?
Actually, it's open. It's an open locus inside of this guy. That's precisely characterized by the property that the number of eigenvalues is maximal. I mean, it's just because whenever you have this kind of counting, then you can show that this function is lower semi-continuous, so there is an open set. and is open only on this guy. I mean, it's characterized by this property.
So you only have to show that it's non-empty.
Yeah, yeah, yeah.
It's best to go in BX or best to go in
BXMT. BXMT. That's a very good point. But we'll not go there. Fortunately, there's no time. But this is a suitable point in general. But an MT. So you consider this decomposition, and what the lemma says is actually. So we have peak, right? Maybe what I want to say is that for any B on U, and it's the same U, maybe. I don't know why I changed the graph. For any B, I have this decomposition, and this decomposition, so for any B, we have this decomposition is induced. It's induced from a finite dimensional Q bar linear representation of empty Q bar, whose isomorphism class is independent of B. So this is the compatibility that I mentioned. So whenever you pick B on this generic open set, then you look to the generalized space decomposition. This decomposition actually is a Q bar representation of the non-Fortic group with coefficients extended to Q bar. I mean, before we're looking to this non-Archimedean story, so you would expect that the coefficients are from bar K, right? Meaning this non-Archimedean. But the point is that you can do better. You can actually come from bar Q. Okay, and the isomorphism class is independent. So now, even this fact, you remember that yesterday we agreed that whenever you have a decomposition like that, then yesterday you could recover some F bundle decomposition. So then locally, your A model F bundle splits locally. Some A models as bundles whose fibers are now these precise representations. The fibers are the representations. So, and definition. The collection. The collection of H lambda, lambda, G lambda are termed local Hodge atoms of X. Local because they come from a given variety. So you start with a variety. You build this A model bundle. Then you look to this locus inside of like this fixed locus. Compute the splitting. You're going to see some decompositions of the homology given by this splitting. You know by a fact that these are representations of the non-Fortic group. If you like, it's okay if you think that these representations are just representations of the non-Fortic or just of one. You make this. These are the local atoms. But now we want to proceed with the motivic nature of these guys.
May I ask,
Yes.
how do you know that you're in this U in general? I mean, how do you check that?
You don't know. That's one of the main difficulties of theory. Whenever you do some example, some computation, you never know exactly if you're computing the right point. In the following sense, suppose that you are given your A model, you know quantum multiplication and you know this kind of story. Now you want to compute the IM values. Then you get some number. For instance, people do this for small quantum homology. How do you know that if you don't move a bit on B, it doesn't split further? That's why it's called atom theory, because they want to keep split further. Like you may have to make sure that they don't. And you don't have like a precise way by looking to the model that it will not split further. You have to do some kind of technique, like there's some kind of Vitali algebra story coming from this other vector field. In many situations, you don't need to know that you are on the final split, that you have a thing the maximal, because you can do.
You can do ad hoc kind of by on the certain example kind of.
Yeah. I mean, let's do some example. Maybe now. Let's do some example now. So let's see. Okay. First, simple. Let's look to x equals to p. It first to the space. Now, the plane is the following. So, plane. The representations of the non-quartate group. So, the local Hodge atoms are all one-dimensional representations of empty Q bar. And how many are there? There are, of course, n plus 1. That's the dimension of the Coulomb. Moreover, these representations. So let's prioritize them by lambda. So these lambdas here belong to the set of n plus 1 roots of unity, actually. And these generalized eigenspaces here, that's denoted just like this. These are the generalized eigenspaces, meaning the representations. They're Hodge homologies of what? Oh, let's put lambda made like that. So some sort of that. My point is that this is splitting the representations come from the same orthogonal decomposition of bases. This is presentation. So let's put that I. This is an example where we can compute. And in this case, the point that provides you the splitting, in this case, what people call by Ismail multiplication to compute the splitting, meaning the point where you're very suspicious. Then another example.
Well, what do you mean? I thought like doing the A model.
Exactly. I mean that's the point is precisely these are representations of the non-quartate group that you can actually identify with Hodge homology of the category of relationships. So there is this question. This is written on this atom Smith symbol. I'm saving it, can't say for myself, where we pose a conjecture relating these atoms splitting and the orthogonal decompositions. I mean, it's tricky. We expected that this happens and that this is true, but we don't know. I mean, looking by some examples, we know. I mean, this is partially also answer-exposed question. And if you look to quadrics, for instance, then you have like the similar orthogonal decomposition. You more or less know how many atoms you want to expect. And you, of course, you cannot fully justify this, but then if you are in a point where you get less than the amount of the objects, then you may like to wonder that you are not on the right place. But is in there. Okay, then another very important example, and this is completely okay. That's the following. Then maybe we could blow up. Another example is the following. Big X, big mesh. Like Calabial, for instance. Then the claim is there is only one atom. Meaning there is only one eigenvalue. But actually here, no matter where you are on the base, we're all be the base. In particular, the generalized eigenspace, there is one eigenvalue, let's say lambda, is the common.
What's that?
Sorry? I mean, so we start with a variety that's NF, then you build this a model bundle. It was
What
is
does
that?
it mean for a variety?
Kind numerically effective.
Like not
Yeah. Like Palladial. The surface of general type. So numerically, yeah, sure. So then the lies like in space. Everything. So in this case, in particular for Palladial, there is only one. Okay. You have to look on the variety when we give this coordinate description. Are all these guys that are Hodge classes, like the coordinates that come from Hodge classes, and that's the best you can say. Sorry. For this example, all classes are algebraic classes and Hodge classes, so that's.
So you want to have a section of the denominator? Because of general type, you might have no section.
Yes,
just
yeah.
and you have the composition.
You look to minimal model and you go to the minimal. I mean, it's really only this proposition is only about DNF. Like, if you have like some surface snap, that's all right. Maybe I wasn't much precise about it, but NF is sufficient. But if you have some surface of general type, then you look to this minimal class, right? And then look to close square NF.
But I thought that you didn't want to have a decomposition. That you wanted to have something that you have for PM.
Yeah, I don't want to do. No.
This is a general type they have decomposition.
Yes. Maybe what I want is that H20 is different from zero.
Yeah, that's fine.
Yeah, I want this. Okay. Surface of general, like a general type of H20. Yeah, that's it. Okay. Now what we have to learn is what this has to do with direction control, right? Because so far, not much. Priori. But then it comes the following. So Itani in 2003, he gave a proof for a blow-up formula for quantum homology. you know that if you pick some smooth center on your variety, let's say that R, the codimension, is greater or equal than 2, then it's quite classical. That's the homology of the blow-up. This is classical. Right? Can be written something like R equals 2, I equals 1, this in here. Right? Then a sort of similar formula holds for quantum homology. That's it. Return says this. I mean, this is classical, not Iritani. Then a combination of using Iritani, then like that. Then AKPY prove the following. So you see that here on this left side, the blow-up is written in terms of the homology of X and R minus 2 times the homology of the center. What is the consequence of Iritani blow-up formula? So denote this A model F bundle for the blow-up by this thing here. This is the A model. Or ZX. And then consider this variety here, X prime, that is the disjoint union of X with the center. Say R minus 2 times, where R is the codimension of Z in X. Then let also H prime, double prime, B prime to be the corresponding A model F bundle for this guy. The conclusion on Iritanis is that these guys here are isomorphic at such properties. In particular, let's put, whoops, I never denoted. So this set here, we denote this set by, let's put atoms. So then there is a bijection between the atoms of a student and the atoms of X, where X student is this guy. So it means that from these decompositions, you know what to expect, and you can try to expect and know what kind of Hodge representations come from blocks. That's the intuition. That's what's going on. So, I mean, myself, and this is because of my perspective. So, I know that when this story started in 2005, Ludmil had in mind the proof of Griffiths and Clemens about the three-dimensional cubic. And the point is that you show that the intermediate Jacobian is not the Jacobian of a curve. So in this case, how you prove the non-rationality results? You show that the representations that come are not representations coming from codimension, except that comes from codimension 2 or higher. So if you want to prove the non-rationality of the cubic for fold, you compute this split. Then you have these atoms, and then you look to the representations there. If there is a representation of the morphotype that doesn't appear as in the analogous decomposition of points or curves or surface, then it's no ratio. That's how it goes. I mean, it's like some kind of grammar vision and Hodge duty in the same spirit of lemons and gifts, but the new stories you put this grammar vision later. But this is how it works. So you have to be able to compute the splitting on a point, show that this point is general or not, and then knowing all the possible splittings that comes from points, curves, and surface, verify that in the case of the cube, this doesn't appear. That's so always keep in mind this the intermediate Jacobian is not the Jacobian of a curve. It's the same thing in sphere. But now you have to keep track all the possible coordination to start up here. Due to this result of it. So then okay, we are good with time. Now that given that stuff, we'll see that we have defined Hodge atoms, right? Local Hodge atoms, then what is Hodge atoms? Yeah. So that's this. Whenever it's because you have a blow up, I mean, not only this, but you have another result of importance that is this thing that's termed quantum Leray Hirsch also exists in Leray Hirsch's whenever you have like projected bundles, you can relate as characteristics on the fiber and the base. Some quantum story also exists. And the point is this goes well with this F bundle story. Same kind of identification. And then we can define atoms, not only local atoms, Hodge atoms. Atoms, what is this? So let's make a huge set, really huge. You look to all the isomorphous classes of smooth projective varieties of C. And then you look to the atoms of these varieties. Then you can show because of Gromov-Witten and our invariant and automorphisms, then it's okay to log out this guy, don't change. And then we start to put some equivalence relations here. The point is that I want to collect all the possible atoms, and now I want to make some identifications between them. I collect all possible smooth projective varieties. I collect all possible atoms, meaning these representations of Q-bar structures, if you like, and I want to put some relations. And the relations are possible because I'm relying on this F-bundle structure. That's the only technical aspect of F-bundle story. In practice, it's really about representations. So you have the atoms, and what are these law of relations? Or what are these equivalence relations? The first is the following, is by disjoint union. Well, it says that if you pick some disjoint union, then for CI, you identify atoms of CI with its corresponding on here. Here, its corresponding. Atom X1. And now, the second, for instance, is Bohr. So you write, you look to atoms of the blow-up. So X tilde is the same as here. You identify where the atoms of X prime coming from this disjoint here stuff. And some similar for letter here, but we're not going there. It's all right. But the main point of this, now it comes the motivic nature of the story, in some sense. Motivic nature, it is for every alpha that you pick on these atoms, then what's going on is that there exists some smooth projective variety X such that alpha can be represented as precisely some generalized eigenspace for the model F bundle of X. So they really come from this kind of representations. And so it makes sense to consider invariants of atoms. Because all this construction seems okay. I mean, we're extending, we have representations to which a model you construct this. But how you actually keep track of these guys to make computation, right? You have to attribute some kind of a numerical invariance to these guys. And this is what I wanted to mention. You have numerical invariance. Numerical invariance. Very following. So you pick some atom. Then you know that it comes from like a generalized eigenspace for some smooth projective variety. So it comes then there is some X such that this guy appears as empty Q bar red in the homology effect. I mean, this is morally what we are saying so far. You can really see this as some kind of a representation coming in the homology of some variety. That's what it is. You can see these guys as representations for some homology for some variety. And then you put this invariant here. That's what is the dimension of, so it's like a generalizing space. Atoms, and then there is such that appears that we denote by V alpha. Is the dimension of this V alpha when you intersect with the Hodge process of is this invariant. Remember, this is a subspacing homology that's also a representation of the non-perturbed line. What is the intersection first? Like how many Hodge classes are in the subspacing homology? This is one of the invariants. The second invariant is for some X, yeah, that you may not know. I mean, that's like, but remember that you took some kind of equivalence classes, and my point about the representations that the representations does depend on the choice of the representation.
And this section.
Yeah, exactly. Good. Hodge polynomial. That is the following. We pick some E alpha T, right? This guy will belong to Z T t minus 1, where the coefficient in the front of decay is precisely the dimension of what? Of this V alpha intersected with HPQX. Dimension of HPQX such that P minus Q is this. Hodge polynomial. These are some invariants. These guys. And essentially, when you want to do something with atom theory, then let's see how it goes computationally. But maybe say the criterion then. So then the notionality criterion. You start always with your smooth projected array. Then you do the Z model story, do the A model story. This is how you compute stuff, right? Actually, you don't need it to go to the models on the story. So it's just an open notification. Then if one of atoms of X does not come from codimension, let's suppose greater than 2, then X is null. So this is the spirit of Clement and Griffiths. And what I mean by doesn't come, in the following sense, that atom always comes from a smooth projective variety. So it cannot come from codimension 2. You do the guy for your smooth projective variety, then you know that it has to come to some other varieties by this kind of aspect. And it comes, for instance, if you're in dimension 4 and comes from stuff in dimension 3, it's wrong. But it could be even worse because you do this kind of identifications, and more importantly, because you're packing together Hodge representations, it could be that these representations come, for instance, for like some legit non-competitive spaces, meaning like are the Hodge representations coming from like a series of gerbs and this kind of story. I mean, it can happen, this kind of stuff. So the main point is that in the cubic case, so 2 words on the cubic case, the 4-dimensional cubic, 2 words, the 4-dimensional cubic. I'll give a proof that's morally right, but it's technically wrong. It's the following. So you pick your smooth 4-dimensional cubic, okay? Then you do this business. You compute the eigenvalues. This claim is true. I mean, I'll say the claim that I'm lying, but more or less lying. I mean, you can do this in the future, maybe. But so you have the cubic fourfold. Then you compute there is a point coming from a classical computation of a given tau that the eigenvalues are 0, and then 3 roots of unity. Then these guys will correspond to some subspaces in the homology of the cubic, right? My claim is that this guy here, and now is the proof, now is the part that is the wrong, because we can never argue like that. We have to use the invariants. But so you have something that almost looks like a K3 circle. Correct the numbers. Never would swing to anyone. Right. So yeah, so we have this piece here, the subspace in homology, is something that resembles the K3 surface. And then you have other one-dimensional spaces, one for each of this root of units. But the cubic four-folded has certain algebraic cycles. Each atom has to have one algebraic cycle. So this is one-dimensional. It has only one algebraic cycle, only one algebraic cycle, only one algebraic cycle. This guy then has the remaining of the numbers of algebraic cycles of the cube. But if you count this number, it's not the same number of algebraic cycles of a K3 surface. So this doesn't come from the K3 surface. That's how it works. Now you have to be able to show that no other surface can contribute with a Hodge diamond like that. You can do this. This is why I said this is not the correct proof, because it doesn't make sense to write this Hodge diamond's property. You have to keep track of the invariants. The invariants that you keep track is the number of algebraic. So algebraic cycles. Yeah. So I mean, this wants to be a K3 surface, but it has the wrong number of algebraic cycles because it inherits the remaining of the algebraic cycles of the cubic. So it has the number of algebraic of the cube minus 3 that we're splitting in the other atoms.
But how do you know the algebraic cycle?
I mean, because in this case, there is this was a proof of Torelli, and then you can show that you can split the homology in a purely transcendental and algebraic variety. So you use the Torelli theorem for very general for folds in this case. But this property that only like always has one algebraic cycle comes because you have representation of atoms. The atoms are representation of atoms.
What do you compute that shows you the difference?
I mean, you do the following. You're gonna keep track the coefficient of T squared, T2, the coefficient of T squared. Then you compute all the possible atoms for curved surfaces and points. Those who have coefficients of T squared different from 0 have to have at least 3 algebraic cycles. In atoms of surface, they have at least 3 algebraic cycles. And that's how it works. Yeah. The point is,
How do you find the algebraic cycle?
no, but in dimension 2, for instance, in curve it's okay, and we can classify this Hodge surface. In dimension 2, they have to use these Hodge polynomials, and they don't know them precisely, but they know, for instance, that for a surface, the limitations they have like under some hypothesis. For instance, you know that surface of general type they have only one atom, right? If you assume H20 different from 0. Now, by minimal model program, they conclude that this atom, that's the full homology, has at least 3 algebraic cycles. So you don't need to know them exactly, but only some estimations. But this is how the proof is computing this kind of invariance.
Hodge class or actual sum?
Hodge classes.
Well, that's a very different thing.
Yeah, I know. But yeah, I know. Yeah, for surfaces, it's the same. So I mean, that's one of the main points about this theory has gone good so far only for dimension 4, because you need to fully understand atoms per surface. And in this case, you can do pretty much because you know Hodge classes and this kind of stuff. You know minimal model program. But if you want to get results in dimension 5, you need to understand the atoms in dimension 3. And this is far from reach. Okay. That's it. Thank you very much.